and we'll start our session 9.
Sir, I hope my screen is visible.
No, till now it's not visible.
So now,
Uh, yes, now it is visible and full screen. Okay, you please carry on. Yes.
okay, sir. Good afternoon, everyone. Once again, I welcome you all to the AI or ML based controllers design and their application in real time platform, which is organized by the Department of Electrical Engineering, National Institute of Technology, Rourkela. Today, I'm going to deliver a talk on advanced power management techniques of a DC microgrid. And currently, I am working as a research scholar under the supervision of Professor Krishna Roy and Professor Arnab Ghosh. Before proceeding, I would like to inform it is a conceptual based and also a laboratory based session. This is the outline of my presentation, starting from overview, further the objectives we are going to achieve. Description of the whole system is given by the basic block diagram. Control architecture for proper power management among the sources like PV, biomass, pico hydro, and the energy storing device that is the battery. Here we have modeled the battery and PV systems. So we will also go through the modeling of the systems. Power flow management for proper load distribution. We will also go to see, and followed by the discussions on the results we got and summary. So coming to basic overview, as we know in today's scenario, there is very much degradation of air quality. The particulate matters in the air are increasing day by day. So we are moving towards the clean energy like solar, wind, biomass, etc., which is not only abundantly available but also available free of cost. But there is a issue of intermittency, like solar, whether it is a sunny or rain. So we can't rely completely upon a single source, that is solar, or any other source like wind, whether the wind speed may or may not be available. So we go for hybridization of the renewable energy sources. These are basically application oriented for remote area locations. Here the controls we have implemented: maximum power point tracking, battery controller, and PWM controller. The control techniques are PI controller, that is optimized with some meta heuristic algorithms, and the pulse width modulation. Here also we have implemented intelligence techniques, that is machine learning techniques for the prediction of temperature and wind speed. Here I have only shown the temperature as it is related to the work. So boost converter, we have taken boost converter for extracting maximum power from the PV. Bidirectional DC-DC converter is helpful for the battery for charging and discharging, which is controlled by the PI controller with some nature-inspired optimization algorithm. So now the objectives for that we are going to achieve: to interface various sources like solar, biomass, picohydral with this multi-input converter. As there are multiple number of converter. We can say it as multi-input converter. To control it with efficient control techniques, the DC link voltage should be regulated irrespective of any load variation, temperature variation, or maybe the variation in solar irradiation. Energy management with control with various intelligent techniques to operate it as a smart system. Managing the charging discharging cycles of the battery and to ensure proper power balance. Here is the basic block diagram of the system that we have taken four sources like biomass, picohydral, picohydral, this is biomass connected with two rectifiers, AC, that is AC-DC converters, and through DC-DC converter they are connected to the common DC link. Similarly, the PV is also connected through the DC-DC converter to the common DC link. Battery is connected through a bidirectional DC-DC converter to the DC link, and we are feeding here a DC load. The schematic of this standalone hybrid system. As we have seen in this basic block diagram, this is the whole internal view like the PV connected with this boost converter to the common DC link, battery with this bidirectional DC-DC converter, but this picohydral connected through a diode bridge rectifier after converting to DC through a buck converter is connected to the DC link. Similarly, biomass also connected through a diode bridge rectifier and through a buck converter connected to the DC link. We are feeding it to a DC load. All the converters are connected through their respective controllers. The control architecture. First, for maximum power point tracking, for the PV, we have considered VPV, IPV with the perturb and observe algorithm. We generate duty ratio. From this duty ratio, we are by PWM technique, we are generating the pulse for the switch. Here VPV and IPV gives us the power of PV power. So this is the whole complete control architecture. VDC is to be maintained. So it is after comparing with this reference value, we are feeding through a PI controller and it generates the average current. This is controlled through a optimization algorithm that here we have taken the multiverse optimization algorithm by controlling the absolute value. The ITA, that is the integral time absolute error, is the error function which is used for minimization of the error. And now all the currents are controlled like for biomass, PV and picohydral. All the currents are controlled. And for the battery reference, we are taking the state of charge of the battery. With this power management scheme, we are generating the currents and and passing through a controller, we are generating PWM for each switches. Now, the modeling of the system. For PV, we have taken a single diode model, that is IPH is the photocurrent, ID is the diode current, RP is the parallel resistance, and RS is the series resistance. The battery system is also designed in a similar way with a control voltage source with an internal resistance. These are the equations of the modeling of the system, where I represents the IPS minus ID minus ISS as shown in the previous diagram. If we expand this expression with respect to all the parameters like RS, RP, we'll get this equation number 2, where VT is the module thermal voltage. And T is the temperature, K is the Boltzmann's constant, Ns is the number of series connected cells, I naught saturation current, and A is the diode ideality factor. Similarly, for battery system, by equation number 1 given by for the battery system, where E is the no load voltage, Q is the battery capacity, and E naught denotes the battery constant voltage, and K is the polarization factor. We have considered two cases where I reference less than 0 and I reference greater than 0 for battery charging and discharging expression, which are denoted by equation 2 and equation 3. So, we have done the forecasting of temperature using artificial intelligence techniques. As we know, machine learning is basically three types: supervised, unsupervised, and reinforcement. Again, supervised is classification and regression, unsupervised is clustering and association. The process of forecasting of temperature begins from data collection and organization of data to filter out the unnecessary data, to build the model, analyze the results, data visualization. If there any discrepancy occurs, then we can retrain the model and transform into visual results, like whether we want in um, graphical form or anything. So into visual results. This is the process which is begin from training the data set. Here I have taken the 60 years of data for training. After training, we did the prediction. If there is any false result, again it will retrain and gives us the correct output. And I have taken 20 years data for the testing purpose. These are the comparison for actual and predicted values of the temperature forecasting, and the mean absolute error for prediction we got using different uh, uh, machine learning techniques like linear regression, decision tree, random forest, support vector regression. Here, using all these supervised machine learning technique, we got minimum error in the case of support vector regression, that is the 3.36. So now the multiverse optimization. Here the concept is basically the black hole and white hole concepts. The multiverse of optimization inspirations comes from the Big Bang theory, which like each Big Bang causes the birth of one universe. So multiple universe interact or collide with each other. So they produce new universe. So white hole that that cause the production of universe. Black hole which will attract everything, and wormhole act as a travel tunnel where object can travel from one universe to another. So basically, it's worked on the roulette wheel mechanism where uh, this is the flow chart of the optimization technique. From starting, first we will initialize the various parameters like a number of universes, random initialization universes. Then we will sort all the universe and normalize the inflation rate for all the universe. And if fitness function of each universe is evaluated, it is initiated from I equal to 1, and we have considered the black hole indexed as I. Then followed by whether we'll check whether the white hole index is equal to the roulette wheel selection or not. Then again it will repeat, and we'll at each step we'll check whether the number of objects and number of universe are satisfying our criteria or not. Then if the stopping criteria is satisfied, we'll get the optimized results. These are the equations for multiverse optimization. Xij, which is equal to xkj, where r is the normal a random number r1. Participants, kindly mute yourself. Thank you. Where j is the jth parameter of the kth universe, where x and xij represents the jth parameter of ith universe, and r1 represents the random values. And the xij given by the formulas xj plus tdr, which is multiplied by upper bound minus lower bound into r4 plus lower bound, where random number 3 should be less than 0.5. And another case where random number 3 will be more than or equal to 0.5, there xj minus tdr multiplied with upper bound minus lower bound into random number of r4 plus lower bound. These are the convergence curves for various algorithm comparisons. Like we have done with three optimization algorithms: multiverse optimization, gray wolf optimization, and fuel optimization algorithm. The best results we got from MBO, that is the multiverse, as it has the lower convergence rate. It converges faster as compared to the other two. These are the KP and KI values we got from the optimization, that is the multiverse. Here for the MBO optimization, we got the minimum, the optimized value, that is 2.92361, and KI 51.9771. This is the Simulink model, where it consists of three sources like PV system, pico-hydro system, biomass energy, and the energy storing device, that is the battery. And these are connected with their respective converters with maximum power point tracking. These are the results we have got. If we vary the load power, here the blue curve is showing the load power. If there is change in load power, that is satisfied by the battery, but the other three sources are maintained constant. Like PV is maintained at 100 kilowatt, biomass and pico hydel maintained at 2 kilowatt, but load is increased from 5 kilowatt. This is the DC link voltage, which is maintained irrespective of the load change. This is the state of charge of the battery during this change in load. Now the variation in PV power. If we vary the PV power while other all the other parameters are maintain constant. So the PV power is the pink one. So this is given by the battery power, which is to satisfy the demand, which is constant here in this case. But to satisfy that load demand, battery power is used to maintain the load. Here also in this case, the DC link voltage is maintained constant, and SOC for this case too, that is change in PV power is represented. Now, if we vary both parameters, like more number of more than one parameters, like both PV and load power, here we are varying in two steps. The load power we are varying in two steps, and similarly PV is also varying in two steps, one at zero point 0.5 and one at 1 second. So to satisfy the load demand, battery also supplies, but all should be in a matched in a proportion manner to satisfy the load demand. The DC link voltage for this case is shown, which is maintained constant, and the state of charge of battery. Now variation in picohydral and biomass gasifier power. Load is maintained constant, PV is also maintained constant. The other two sources are varying in like a complementary fashion, and to satisfy to satisfy the load power, that is the remaining power will be supplied by the battery. DC link has to be maintained anyhow. That is our main objective, and the SOC, the state of charge, is also represented. Now, this summary, I want to summarize the session. The boost converter is controlled with MPPT controller so that maximum power can be extracted. PI control is also implemented for the bidirectional DC-DC converter. DC link voltage is maintained irrespective of any change like in solar radiation or load or source. For optimized results, PI tuning done with that multiverse optimization technique. Uninterrupted power supply also ensured using the battery, and power management with the energy storage device, that is the battery, is done using a bidirectional DC-DC converter. These are some of the reference I have gone through. So thank you. Now I'll give a basic idea about the controller we have using. I hope the screen is visible.
Yes, it is visible. Just make it full screen.
Yeah.
Yes. Ah,
After the after validating the model in Simulink platform, we have also done with the hardware part. So for that we have used the C2000 microcontroller and the family F28379D. So I'm going to give a brief idea about the controller. These are the overview, introduction, about launchpad pin and its description, GPIO modules, EPWM modules, generation of carrier wave for DC-DC converter and inverters, ADC and DAC module, conclusion. The real-time microcontrollers are scalable real-time controllers platform designed mainly for efficiency in power electronics devices such as high power density, high switching frequency, and also for GAN devices. We are generally using from SIC, but we can also use for GAN devices. So it mainly works. It has four functions like sensing, controlling, processing, and interfacing. For sensing, it gives us very high accuracy as compared to other controllers. It's a 12 by 16 bit ADCs up to 24 channels, full analog comparators with built-in DACs, quadrature encoders, and capture logic. For control, it's highly flexible with high resolution. Up to 32 outputs we can see, tightly coupled with sensing domain and fast response time. Buffered output DACs are also present. For the processing, it's very highly, it has high performance. Floating point DSP, it is with C28X core plus parallel multi-core architecture. Instruction set optimized for control max up to 925 MIPS. Integrated communication circuits like CAN, CAN-FD, EtherCAT, XCMIF can be interfaced with this microcontroller. These are various families of this microcontroller. This is the comparison among all these controllers. We have controlled on the basis of performance with flash size, with respect to the flash size, which varies from 150 MIPS to 600 MIPS. So we have chosen TMS 320F 28379D for its higher accuracy, high performance CPUs, and it has two CPUs up to one. It gives 800 MIPS up to 1 MB. The controller features are it's a dual core architecture, clock frequency 200 megahertz. Time it takes time for execution of one instruction is 5 nanoseconds. It's a 32-bit processor and has both a floating point multiplier unit and a fixed point multiplier unit. Trigonometric math unit CPU's performance is further boosted. It enables fast execution of algorithms with trigonometric operation common in transforms. It has also various complex units which reduces the computing time. Two programmable control law oscillators also execute code independently. On-chip memory is 512 KB or 256 kilowatt or 1 MB, 512 kilowatt of flash, and for RAM 172 KB or 86 kilowatt or 204 KB or 102 kilowatt. The system peripherals, two external memory interfaces, dual 6-channel direct memory access, that is the DMA controllers, Up to 169 individually programmable multiplexed general purpose input or output GPIO pins. Each CPU has 14 peripheral interrupt lines. Out of 14, two of them are interrupt 13 and 14 are connected directly to the CPU timers 1 and 2. The remaining 12 are connected to peripheral interrupt signals through the interrupt expansion module, that is EPI. The communication peripherals, USB debugging and programming interface by a high speed galvanically activated debug probe. Two control area network modules, three high speed up to 50 MHz SPI ports, two multi-channel buffer serial ports, four serial communication interfaces, two I2C, that is inter-integrated controllers interfaces. The analog subsystem it consists, that is of up to four analog to digital converters, that is ADCs, single, simple, and hold on each ADC. 16-bit more differential inputs are two types, that is one is 1.1 MSPS each, up to 4.4 MSPS system throughout, and up to 12 external channels. Then for 12-bit mode single-ended inputs, one is 3.5 MSPS each up to 14 MSPS system throughout, and at the other is up to 24 external channels present. 8 windowed comparators with 12-bit digital to analog converter references are also there. 3 12-bit buffer DAC outputs. Then enhanced control peripherals, 24 pulse width modulator channels with enhanced features, 16 high resolution pulse width modulator channels. Again, it's two kind of like high resolution on both A and B channels of 8 PWM modules. Deadband support on both standard and high resolution. 6 enhanced capture, that is ECAP modules, where accurate timing of external events is required. Then 3 enhanced quadrature encoder pulse, that is EQEP modules. Like it can give us information about position, direction, and speed for position control systems. This is a picture of this TMS 320F 28379D launch pad, where J1, J3, J2, J4, J6, J8, J5, J7 at the jumper pins. JP3 that connects from USB, which used for disable of isolation, and JP2 that is ground from USB, that is also do the same function. And this S1 which boost modes, this is the chip, that is the main chip of the, that is 37 and 9D. This is J14, J15, J12. This is the pin overview. This is I'm not going through in details. In first half, also one of my colleagues also shared a detailed discussion about this 3790. So I'll go overall. Similarly, this is this is also the pin numbers, like J1 and J3 pins at the GPIOs, and here the ADC channels. From ADC like for C, B, A, these are present for J3 pin. Similarly for J4 and J2 GPIOs, which also act as GPWMs, and JF12 also. Now this is continue the launchpad overview. Similarly, the jumper pins like J5, J7, J8, J6, J5 from 41 to 50, J7 from 61 to 70. Similarly, for J8, 80 to 71, J6, 60 to 51. These are the on-chip modules: GPIO module, timer module, EPWM module, DAC and ADC module, QE, QEP module, memory and clock module, and communication peripherals. The GPIO pin is an uncommitted digital signal pin on the MCU, that is the microcontroller unit, which can be used as digital input or output. GPIO pin are multiplexed and operate as digital input or output, or connected to one of the three peripheral input or output signals. This controller has 169 GPIO pins and grouped as 6 ports. So first 16 bits 0 to 15 are accessed through MUX 1 and remaining 16 bits accessed through MUX 2. Like port A consists from GPIO 0 to GPIO 31, 32 pins. Port B consists of GPIO 32 to 63, 32 pins. And port C consists of 64 to 95, 32 pins. D, GPIO 96 to GPIO 127, 32 pin. Similarly, E, GPIO 128 to GPIO 159, 32 pins. And port A consists of only 9 pins. The registers present in GPIO like control register and data register. 0 configured as input and 1 configured as output. GPIO data register generally indicates the current status of GPIO pin, and GPIO port basically operates three functions like set, clear, and toggle. For that, instructions use the GPX set, GPX clear, and GPX toggle. These are the registers present for this specific task. After the MATLAB interfacing, these are the outputs we have got. Like this, it is duty ratio equal to 50% and operating as this is the pulse generation for a boost converter, or we can say any DC-DC converter. This pulse generated using GPIO pin. We have also generated sawtooth waveform using the C2000 microcontroller. The PWM generation, that is the enhanced pulse width modulator, EPWM. It is basically a method for representing an analog signal with a digital approximation. The PWM signal consists of a sequence of variable weight, constant amplitude, pulse, which contain the same total energy as the original analog signal. Means there is no loss by transferring the signal from input side to output side. And this controller has six pulse width modulator channels and 12 pulse width modulator outputs. And one complete PWM channel composed of two PWM outputs, EPWM A and EPWM B. It has a dedicated 16-bit time-based counter with period and frequency control. Each EPWM module consists of 8 submodules such as time-based counter, counter compare module, action qualifier module, deadband generator module, PWM chopper module, treat zone, digital compare, and event trigger. So now this block diagram, that is the structure of the C2000 control. Here the EPWM clock is fed and to this 16-bit time-based counter. So TB clock or the clock frequency of the controller, that is period to set back after counting. This time-based counter represent basically this function. And this compare registers, that is here modulation index is stored and there are two compare register. This is A and this is B. And the action qualifier, it takes the decision that what action must be taken, like set, reset or do nothing, while generating the enhanced pulse width modulation. And the dead band, dead band is the I can say the main advantage of this controller. Like for inverter operation, while we are operating in a single leg for a single phase split inverter, in a single leg there are two switches. From the time gap between from on to the from off of one switch to the until another switch on, there should be a time gap. Otherwise, a dead short circuit may happen. So that we use this deadband unit. And this event trigger, that is basically fed to the ADC channel for triggering another or multiple events. This is basically up counter and this is the down counter. This TB clock, this time gap between 0 to 1 is represented by this TB clock. And how many countings to be done decided by this TB PRD at each rising age. And it increases the count gradually. And this TPWM formula is given by TVPRD plus 1 multiplied by TV clock. Similarly, for down counter, uh, the same formula and here also, but the action qualifier will change its values like set, reset, and toggle operations. This is of down counters. Here, two timers as we are counting twice, so that one in previous formula there is an one, so it will be eliminated for this up and down counter. So how to calculate this EPWM clock? EPWM clock is the system frequency divided by 2 and the system clock frequency is 200 megahertz. So this EPWM clock will be 100 megahertz. And TV clock is calculated by EPWM clock divided by HSPC clock multiplied with clock divisions. These are basically choosing like one one multiplied with one or two multiplied with two. Like depends on our requirements. Here is the table that given for some reference. Now, as I earlier said, EPWM consists of 8 submodules. Now, action qualifier, the action qualifier submodule is the key element of this EPWM, which basically takes the decision, and it utilizes to match the events from the time base and the counter compare submodules for performing actions on two channels, two output pins, that is EPWM E and for EPWM B. So this action qualifier, it is a 16-bit register. Here from 1 to 0 defined by when action equal to counter equal to 0. Similarly, 4, 5 represents CTR equal to CMPA on up count, and CTR equal to CMPB for up count, and this 10, 11 is for down count, and 6 to 7 is also for down count. These are the codes used for CCS programming while doing the coding in Code Composer Studio for interfacing this C2000. We generally use the digital codes. So 00 represents do nothing, 01 represents to clear or low, and 10 is to set, that is high. 11 represents to toggle, that is low to high or high to low. So this is the comparator, how the C2000 compares the uh, various with comparators for generating PWM. This is upcounting. This is the upcounting. Here, two comparators we have taken, CMPA and CMPB, TBPRD, and this is TBCTR. So first 0 for EPWM1, it is 0 means it will be set at when EPWM1, when TBCTR will be 0, it will be set so that it rise. And then coming to comparator B, that is CMPB. Here it will be do nothing so that it will continue. And at comparator A will clear so that it will go. There is the falling edge. Similarly for EPWM B, this is 60%, this is 30% width. For EPWM-B, it is for 0, it will be set. When TBCTR equal to 0, it will be set. When counter compare equal to CMPB, it will be clear. And when TBCTR will be equal to comparator B, it will do nothing. So that it will be continuing. Similarly, for up and down counter, we compare for two signals, EPWM A and B. This is the pulse we got for a buck converter. Here we have generated two pulse of duty ratio 40 and 60%, operating at 10 kilohertz. Channel blue is represented channel 1 and red channel 2. So the amplitude is around 3 volt, which these are the some of the references I have gone through. And coming to laboratory session, we'll continue.
Excuse me, sir, voice is not audible.
Yes.
Ma'am, the audio is not audible.
Please give me 5 minutes. I'm looking into it.
Clear होगा?
Uh, Hello everyone. Uh, I think there is some glitch, so I'm going to show that live session again. Thank you for your patience. Is it visible?
Yes,
No.
visible.
No,
No, no, no, no, no, no, no. Not visible.
I hope now it is visible.
No, ma'am. Yes, now visible.
visual.
Good afternoon everyone. Now I'm going to start the laboratory session. That is basically the working of the buck converter. So this is the buck converter. Here the supply I'm giving from the input supply, that is from a DC power supply, that is rated at 25 volt 5 ampere. This is the input capacitor, which is around 100 microfarad. And this need not to be very large as the input ripple is low. This is our switch. This is from Infineon and it is rated at 65 ampere. This is the heat sink associated with the switch so that it can absorb the extra heat and for protection of the switch. The protection devices like the heat sink and the snubber. The snubber is basically to absorb any sudden rise in surge voltage across the switch for protecting the switch. This is inductor. It is designed for 25 kilohertz and ETD. It is ETD 65. The bobbin is also a 24 pin ETD bobbin. And its value is around 700 microhenry. And we have used leach wire, that is the white color wire, for this inductor to avoid any leakage inductance. And this is the output side, and this is the output capacitor. Output capacitor is need to be large, so we have chosen 1200 microfarad. And this from this output side, we have connected a resistive load. This resistive load is around 300 ohm. Now this is the driver circuit. This is also the compatible chip from Infineon for used for driving this switch. Uh, this is the DC-DC converter that is for converting one voltage level to another. Like this driver is designed from for plus 15 and minus 7 volt. This driver supply is given from this SMPS, that is 5 volt. This for driving this driver circuit, we are using this C2000 controller, that is TMS 379D. And here we are using the 78 pin number. This is the pin number 78. Here it is connected, this white jumper wire, it is connected to this driver for giving the pulse, that is EPWM. And this is the ground. This brown color jumper wire is from ground, that is for protection. And these three, one orange, yellow, and green wire, that is for that is connected to the switch for giving the pulse. And this we have chosen 78 pin. Basically, the 78 number pin is the EPWM 5. Here we have choose the EPWM 5. This is the TMS 379D chip, and these are the two codes. As I explained in this before some time, this is our microcontroller. Here we are driving this controller for zero point 0.6 duty ratio, and at 25 kilohertz, that is 9999. As my friend Gaurav has already described how to calculate this value for 25 kilohertz in the previous session. And this is EPWM 5, that is for 78 pin. That's why we have connected to 78 number pin. This is basically interfacing of C2000 with MATLAB. We can also use by doing coding with the Code Composer Studio. Now we'll start our experiment. Here you can see the pulses for 25 kilohertz and zero point 0.6 duty ratio. Now we'll give supply to the buck converter. As it is shown, it's 6.77 volt. There are some network issues. I am explaining again. I hope now it is visible.
Yes, ma'am.
Yes, ma'am.
Okay. Now we'll continue from where we left. So now I'm giving gate pulses of 25 kilohertz and duty ratio of 60%. Now we'll give supply to the buck converter, that is 10 volt DC supply, and we'll see the output like 6.79 volt. The buck converter gain is V naught by Vi is equal to D. So for 60%, we'll get 6 volt. Around 6 volt we are getting. So hence we have validated the circuit, and similarly for other converters also we have tested. Like for boost, we have also tested MPPT for PV in this hardware setup, and for other biomass, and similarly for other, but it is not possible to show each and every converter. So I hope this will help you guys in some manner. So thank you. Thank you so much. So any queries from the audience side? I hope there are no queries from audience side. So I would like to end the session. Thank you everyone.
ती वर्कशॉप आहे एवढं मोठी आहे मी एवढा मोठा चहा घेऊन आलो डबल घेऊ आता पुन्हा संध्याकाळी 1-1.5 तास बसतो नाही आता अण्णा बसू द्या पुन्हा आता कसं होतंय 4:15 झाले पुन्हा बस गेलं का बाहेर 4:45 होते 1 अर्धा 2 तास बसू द्या हो चला
So from 5 p.m. onwards, there is another laboratory session. So thank you.
बोला म्हणे हो पाठवलं. आता पाठवलं.